Great. So thanks everyone for being here. And we've got a great introduction by Ayla and Scott for the motivation and background of configuring fully coupled Aqua planets and other simplified geometries within the CESM framework. And I'm doing I'm joining this part of the work as part of my thesis research, and the work has been done with a lot of support from my advisors, Kevin and Chris, as well as a long list of collaborators. I see many of you in the audience, in and out of NCAR. So a big shout out to all the help that we have gotten. And so just to reiterate what Ayla has already mentioned, the motivation for kind of filling in the gap in the hierarchy of simpler models, especially in the coupled sense. So to look back on the atmospheric component for a bit, as Ayla introduced, there is an entire hierarchy of simpler models, simple models for the atmosphere, and the simplified model that's like sort of sitting on the top of the hierarchy already, that's like right next to the full comprehensive CAM, is an atmospheric only aqua planet that has the full sets of atmospheric dynamics and physics, but with a simplified boundary condition in terms of a simplified SST profile that's typically zonally uniform. And there is a set of protocols called the Aqua planet experiments that has a set of typically used curves that in some regards idealizes from the observed real world, and they typically have the SST maximum right on the equator. That's what we get from the real world, and we will look at that a bit more later, what happens when it's coupled. So that's on the atmospheric side. We have the full aqua planet with either prescribed or a slab ocean configuration. On the other side, for the ocean component, there is also a long history of idealized configurations used both for model development and for investigating some of the fundamental science questions, such as the role of ocean geometry in impacting the ocean circulation and the overall climate. And MIT GCM is one of the models that's widely used for this kind of studies, which gives us a lot of insights. However, those studies were typically using a very simplified atmosphere that is, in some regards, you can see it as a slab atmosphere. So both of these components, or both sides of these idealized studies, do tell us a lot of important science information. However, if we want to look at the other end of the spectrum, which is the fully coupled CMIP class models that we use for climate assessments, then obviously we see a gap between these kinds of compartmentized idealized models leading up to the fully coupled and comprehensive Earth system type of models. And that's where our work comes in the regard of using fully coupled CMIP class models, but with idealized configurations in terms of the boundary condition. So we have idealized geometries that's both including the full or the quasi-aqua planet and idealized continents. And to show one of those aspects which could be investigated by this kind of idealized setups include the impact of ocean geometry on the meridional heat transport. So here is just a quick snapshot showing the kind of Earth observation used in CMIP simulations and our idealized Ridge and Aqua planets. And we already see some curiosities in the SST, and also how in many regards the meridional heat transport on the idealized planets don't look too different from the real Earth, although there are some differences, especially in the tropics, that we will look into later. But this is just to further show that despite the extreme simplification, those setups can help us do important science questions. To get into a bit of detail on on how we configure these models, as Ella already mentioned, the atmosphere component we're using is CAM4. That's mostly motivated by a balance between the complexity and the cost. And for the ocean model, we are using the latest CESM component, MOM6, at nominal 2 degrees resolution and about 4,000 meters depth. And we put in the bottom topography there, which is particularly important for the Aqua case. And the rest of the components, sea ice and land, we were just using CESM default. We're really looking forward to having the simplified land model, which would make the process much easier. And for our experiments, we retain the seasonal cycle by using fixed or idealized orbital parameters, and we initialize the ocean state from previous idealized experiments provided by Pedro. So our model, well, with the particular set of parameters, we get pretty close to quasi-equilibrium in terms of the top of the atmosphere balance by year 400. So for the rest of the talk, we will be looking at the 100 years climatology between year 400 and year 500. This is a quick animation showing the monthly SST at year 400 for both this Aqua and Ridge planets. On Aqua, we observe something that's very different from the assumed atmosphere-only kind of SST profiles, in the sense that we have a persistent global belt of equatorial upwelling. So we always get a SST minimum right on the equator throughout the seasonal cycle. And if we look at Ridge, then in some regards we can see it as an idealized gigantic Pacific, and we see some analogs to the features that are in the Pacific, including a western warm pole on the western side and the eastern cold town with the upwelling. And we also kind of see how for the eastern cold town, the advection from the eastern boundary currents also contributes to that, which show the effect is more dominant in some seasons than others. Right. Getting a closer look at the climatological sea surface temperature, the first thing to notice that is both our planets are pretty warm, and Aqua is even warmer than Ridge by 2 degrees. And at those temperatures, we don't get sea ice, and then the planetary albedo is mostly dominated by the effect of clouds. And as we've seen in the animation, Aqua has a global cold belt of equatorial upwelling, and in Ridge, that extent of upwelling has been reduced to the eastern part, and the contrast, the zonal gradient of SST in the equatorial region on Ridge corresponds to the wind stress pattern on the surface. And looking in the vertical at the equatorial thermocline, we see that on Aqua, the global equatorial upwelling corresponds to a really shallow thermocline on the right in the equatorial region, whereas on Ridge, this is a very sharp contrast that due to the presence of the western boundary, we see a thermocline that's more Earth-like, and again, the depth of that thermocline reflects the convergence of the zonal wind above. And we see the location of the warm pole being about a third way across the ocean basin. And that's a question that we're still trying to understand, like what are the controlling factors in the intensity of and the location of the western warm pole? That's something to investigate. And looking at the ocean circulation in the vertically integrated sense. So here we see the barotropic stream function being overlaid on the zonal anomaly of SST. And Aqua, we see very little zonal anomaly as we designed it, except for the imprints from the bottom topography, and which is more easily shown in the higher latitudes. And Aqua just have this massive zonal flows. In the Ridge case, that is dampened a lot, and the magnitude of the flow has been reduced, and we see the more familiar double gyre kinds of kind of circulation with the warm part and the cold town in the background. To get a better look at the zonal flow at on these two planets, here we're looking at the zonal average of the zonal flow, and again on Aqua we see how we just get these crazy zonal jets, and the maximum velocity definitely reaches a magnitude that's not very Earth-like. In the Ridge case, that is much reduced, and we get a lot of interesting features, especially in the tropics, that we have analogs to the equatorial under and the counter currents, and which corresponds to the depths of the equatorial thermocline at about 500 meters, and that's another aspect where the presence of the western boundary immediately brings us more Earth-like or Pacific-like features. And the presence of that zonal asymmetry on the Ridge planets leads to asymmetry in the atmosphere as well. And here we are looking at we're looking in the atmosphere and looking at the zonal circulation in the equatorial region. In the Aqua case, the cold and dry equator corresponds to a belt of subsidence, whereas Ridge again looks more familiar with a Walker-like circulation with convection over the western warm pole and subsidence on the eastern side. And that leads to or contributes greatly to the overall difference in the climate that we have seen. Looking at the top of the atmosphere balance, Aqua receives more incoming shortwave and the total amount of equatorial, tropical surplus than Ridge, which requires the overall heat transport to be greater. And looking at the heat fluxes at the ocean surface, here we see that the main differences, especially right in the equatorial region, between the net heating between Aqua and the Ridge, is that Aqua receives a lot more net heating, which is mostly due to the greater amount of shortwave, as well as lesser amount of latent heat loss. So in other words, the dry equatorial belt on Aqua, despite it being cold, it's actually a region of heating for that planet and compared to Ridge. And those energetic aspects tell us something about how the overall meridional heat transport should behave. And now we are looking at it from the dynamic side of how the meridional overturning circulation actually transports this heat for both components. Here we are seeing the meridional overturning circulation in the solid and dashed contours, and the color shading underlying both of them are the stratification of the energy, which in the atmosphere scales with the moist static energy, which again scales with the equivalent potential temperature, and for the ocean it's just the potential temperature itself. And for the overturning circulation in the Aqua case, we see that the cold equatorial belt, or the SST minimum on the equator, gives rise to some alien features, which are little reverse Hadley cells. And so the regions of convection, or the double ITCZs, are actually we get these two meridionally symmetric regions of convection around perhaps 10 degrees north and south, but subsidence right on the equator. And on ridge, this pattern of reverse Hadley is much suppressed due to the presence of the western warm pole. So that's just gives us a thought of how, in this simple experiment of adding one ridge, gives us some thought on how the realistic ocean geometry actually controls the overall climate and gives us the maximum SST on the equator and the other features of circulation that we see in the real planet. Now, on the ocean, for the ocean side, the thermal stratification and the meridional overturning on Aqua looks pretty un-Earth-like in terms that we get a really deep thermocline in the subtropics associated with how, because of the lack of a meridional boundary, how the overturning circulation is basically goes through the half of the hemisphere, and the upwelling water at the equator returns from substantial depths, and the thermocline in the subtropics protrudes really deeply. So there is a greater contrast of the between the upper branch and the lower branch of the overturning circulation, and that's how the ocean overturning moves more heat around. In the ridge case, we see that because of the western boundary, the thermoclines gets a lot shallower, and that in turn influences how the overturning transports that energy as well. And to tie it up, revisiting the meridional heat transport calculated from those two components, and we see that consistent with both the energetic constraints and how the dynamics was working on the Aqua planet, the atmosphere is actually moving energy equatorward within the 10 degrees north and south, and that is both energetically required in terms that the ocean net heating was greater than the top of the atmosphere heating in those regions, and dynamically that's carried out by the reverse Hadley circulation in the atmosphere. On the rich planet, we still get a little of that wiggles inside of the deep tropics, but that is much reduced from Aqua, and that again, that's in terms of the energetics and in dynamics that the reverse Hadley cells turn to be a lot weaker. So to put down a couple of points of discussion at this point is that despite the simplification in the overall geometry, the climates of the coupled Aqua and rich cases show some features which are relevant to understanding the comprehensive realistic type of simulations in terms of how the ocean geometry impacts the overall climate state, as well as features like the meridional heat transport. And as Ayla previously mentioned, this couple simple models is planned to be available within the next release of CESM with the efforts on the software engineering side to provide tools to streamline this kind of processes, so that investigators can configure their own setups to the question of their interest. And some ideas for the applications for this type of models. Of course, for the interest of coupled atmospheric ocean dynamics, it's helpful to have a full comprehensive atmosphere that could be coupled to an ocean of choice. And the advantage of having a comprehensive atmosphere is that we will be able to represent a whole spectrum of atmosphere phenomena on different scales, including synoptic storms like extratropical and tropical cyclones and how they might interact with the ocean. And on the ocean side, the other track of studies inspired by the MIT GCM series of studies is to explore increasingly complex geometries and how those affect the ocean circulation and other aspects of the climate. And on that, we will hear more from Sarah, who's talking next, on other exciting things like the AMOC. And so that's on the general state of the mean climate of these idealized models. And before taking questions, I just wanted to show a couple of more things which are under investigation, but I think are really curious to look at. So we have looked at the mean state. However, there's also a lot of interesting variability on these planets. One of them is interannual variability in SST that really, I think, looks a lot like ENSO on the Ridge planet. And here, the top plot is showing the first principal component of the Equatorial SST, where we see the region of a dominant variance being in the eastern cold town. So that's a pretty ENSO-like pattern. Although the frequency doesn't quite line up with the realistic ENSO, but it's a reasonable timescale, and that's something we are trying to explore a bit further. Another aspect of variability on the atmospheric side, that is the seasonal to subseasonal variability. One of the dominant nodes being the Meridional oscillation. And I guess this is probably less familiar with most oceanographers, but this is just showing the a spectrum of equatorial modes, which is taken between the 15 degrees north and south, and looking at high frequency, meaning 3-hourly precipitation. And MJO is this guy right here, and that which distinguishes itself from the Kelvin waves, and that's something unique to Ridge that we don't see so much on Aqua. So that's another curious aspect. And one last thing I wanted to show, just because we mentioned scale interactions, is that one of the major motivations to use a comprehensive atmosphere like CAN4 is that we get something like tropical cyclones. And this is using the sea surface temperature from the Ridge experiment and using those to force a high resolution, meaning quarter degree CAN4 only atmosphere, where we see that from the western warm pool in the summer season, we see the emergence of tropical cyclones, in this case 3 of them, which again is it's not too far from what we expect from what we observe in the Pacifics. And in the tracks from 1 year, we see the kind of asymmetry between the western side and the eastern side in triple cyclone genesis. So that's the further direction that we're looking at. And that's just one final example of showing the presence of scale interactions and potentially looking at the interactions of these systems with the ocean. And I'd like to take any questions.
Okay, thanks, Xiaoning. That was great. Questions for Xiaoning? I can't see everybody on the grid, so if you have a question, either speak up or post in the chat that you wish to ask a question.
Hi, I have a question.
Go ahead, Pedro.
Well, I have a bunch of questions. It's so good to see the simulations and see a lot of the features that I found in mine, which are quite different from Marshall's first aquaplanet simulations. I saw that when you showed the zonal currents in the Aqua simulation, the color scale was saturated. So
yeah.
What is the maximum speed that you found on the equator, on the surface, where currents strongest? Mine were ridiculously large, like 4 meters per second.
Yeah, mine is with the MOM6, it's not. It's still pretty large. Let's see on this slide. Yeah, the maximum is like more than 2 meters per second.
More than 2, yeah.
Yeah.
And I haven't been able to slow them down, so I play with the bottom drag and increasing them by orders of magnitude, and they stay the same. So it's something I still don't understand. I thought they would be controlled by the magnitude of friction on the bottom. And my other question is the Walker circulation in the ridge stable, or like, is it always like the whirlpool to the west and the Colton to the east?
By stable, do you mean with regard to interannual variability?
Oh no, more like, well, with the interannual variability that you showed doesn't seem that large, right?
Mm-hmm. Right. The magnitude is pretty small.
The configuration. In some of these configurations, you can switch sides, and you end up having the whirlpool in the east.
Really?
Yeah. And I have a third question. You run them for 500 years or for 400 years. What's the drift that you have? I'm surprised you're not having a lot of drift starting from my initial conditions, given that your climate is so much warmer. Mine, I tweaked some of the parameters in the atmosphere so that I would get a global mean temperature of 14 degrees. I thought it would, these are entirely subjective choices, but I thought that having a global mean temperature closer to observing on Earth was a more desirable feature of the simulation. But are you seeing any drift? Do you have an idea of what the drift looks like?
That's a great question. I didn't put the plot here, but by the end of year 400, the drift in terms of both TOA balance and the ocean potential temperature was pretty small, like pretty negligible for both of these planets. So our deep ocean is still drifting as we expected, but the overall climate is not that bad. And another part of your question on having more Earth-like temperatures, and in some regards that translates to like more Earth-like albedo. That's certainly one of the aspects that we can like so to speak tune into for the idealized worlds. However, we just felt that because of their well, even though they're idealized, there are still a lot of degrees of freedom, and we can always try to line some aspects more Earth-like opposed to others. And in our case, we think the absence of CS is not the worst thing. We can we get all the action from the atmosphere, and in terms of the meridional heat transport, which is what we are looking at, it's already pretty Earth-like. So we think it's a reasonable configuration for our question. Even though for other questions, where a Earth-like meridional temperature gradient is more desirable, or if CIS is more desirable, then there are reasons to go to tend to those dimensions a bit more. That's like our rationale.
Yeah, that makes sense. Last question. I don't want to take all the time. Are you planning to do the simulation running for much longer to see what the real equilibrated climate looks like?
Not at this point, because we are happy with the quasi-equilibrium climate, and a large part of that is a data management issue on top of the computing hours. So yeah, if there's infinite like space, then maybe it would be curious to see what happens. Oh, and along those lines, there are these MIT-GSM studies on like multi-equilibrium states. You can like perturb them and things like that. So on the millennia scale, that there would be some interesting things to see. But for now, we're settling with this quasi-equilibrium that we have got.
Yeah, that's intriguing, because my simulation had a transient at the beginning, at the first 1,000 years, in which it didn't have any sea ice, and it was because the Equatorial Ocean had such strong upwelling that then all the energy balance is at the equator instead of at the poles, and that's why you have that dry zone on the equator. It's easier for the climate to emit radiation back to space on the tropics. So I wonder if the sea ice could still grow if you keep it running. At least in my simulation, the ice came back as the equatorial upwelling weakened. And there's some research showing that they are related. Richard Seeger has a paper showing that sea ice and the strength of upwelling are related on this planetary scale.
Yeah, that's certainly an interesting thought. And Robert has a question.
Okay, Bob.
Thank you. Nice presentation. A lot of kind of oceanographic studies along these lines would take as their next step of reducing their idealization, adding a Drake Passage, although usually with some kind of a deep ridge, or adding a wider Pacific and a narrower Atlantic basin. Have you thought about what your next steps are going past this first very idealized case, and how that might fit into this previous literature?
Right, great question, and a great segue into Sarah's talk next on an increasingly complex form of idealized geometries. For questions like AMOC and a lot of others, we would need a smaller basin to represent those. For my question, which is actually on the interaction between tropical cyclones and the ocean, we are happy with the big Pacific, and we're just going to look at the Pacific-like kind of actions. But I think the purpose of putting this infrastructure in CESM is that all these other configurations and other questions could be explored by this kind of setups, and our Aqua and Ridge is just like a very first baseline.